On homework number 1, the best thing to do is when you're looking at these two problems 1 and 2 is just to look in section 1.1 of the textbook. Problem number 3, you'll have to use a few equations for that. The first one is if the current is equal to the charge divided by time. You simply just solve for the charge in coulombs there. To find the number of electrons, you take the amount of charge that you have computed, divide by the charge of the electron. That is the constant that is given in the statement of the problem on page 39, problem 1.5. And so the charge of the electron, negative 1.609 times 10 to the minus 19th, I think. And you might even need to use this, that an amp is equal to 1 coulomb per second. On page 2, there's a little bit of calculus involved here. You're primarily going to use this one right here and that one over there. So when you take the derivative of an exponential, the coefficient just comes out in front. And so that's what we're going to be using in, I think, one of these problems. So 4 and 5 are very similar to the example problem 11.1. So let me just work that one out for you. This can be found on page 10. Example 11.1 looks something like this. I wanted to point out that your textbook does leave off the units, so I'm going to put those in. There's a coulomb right here, coulomb right there, because that's charge. And to make the units up here, well, unitless, you really have to understand that there is a 1 over a second there to cancel out that one. They leave that out of it. They leave the units out of these problems. What you're asked to do is to figure out what the current is. The current is equal to the time derivative of the charge with respect to time. And so when you take the derivative of this first term, there's no time dependency at all. So you just get a 0 for that one. You take the derivative of the second term, and you get, well, you still have the minus 2 coulombs there. And then, just like we saw at the top of this page here, the coefficient comes out in front, and then you have the rest of the term. And so the coefficient is minus, and don't forget the minus sign, 1 over, 100, and then the units is 1 over a second. And then we need the rest of the term there, e to the minus 100 times time. Alright, so finishing off the problem, you're going to combine the two coefficients in front and realize that a coulomb per second is an amp. So you're going to get 200 amps, e to the minus 100, 1 over a second times time. Make sure you do include your units in these problems 4 and 5. You might notice that there's two problem numbers 5, so I'm sorry about that. In the second problem number 5, all you really need to take advantage of is that they're using lowercase w for energy, and that's equal to power times time. For problem number 6 on page 2, it asks you to take a look at example problem 1.2, and I'm going to do that with you right now. One thing to realize when you look at these figures in this example problem, they have this rectangle here, and what that's supposed to represent is an unspecified circuit element. That means you don't know if it's a resistor or a battery or whatever. So you have to figure it out just based on well, what the currents and voltages are. In this first example, we have the current coming into the positive side of this unspecified circuit element. And so what that means is, since that is happening, that if this were a battery, the positive side of the battery would be here, negative side would be right there. And since I is always the flow of conventional current, the flow of positive charges, we're basically, if this were a battery, we're charging it up. So they're going to refer to that as a power greater than or equal to just greater than 0. And that's going to mean that this is going to be absorbed. So that means that the energy is being absorbed by this element. You're basically charging up a battery. If you look over here at the second example, B, unspecified circuit element B, the positive current is coming out of the positive side. So this is a case where the power is less than 0. So that means that this element, if it's a battery, it is now supplying current rather than absorbing it as it was in part A. On part C, they're trying to trick you a little bit because they change the direction of the elements here, the positive and negative terminals. They changed the sign of those from the previous two cases, and they threw in a trick down here. They put a minus sign on the -3, which means that in this drawing the current is really not going this way, it's really going the opposite direction, and I'm just going to move it. So that means it's going to go this way, and I'm going to move it down here, so that way you can see that it is leaving the positive, and then you just compare it over here to this one, and that means that if you have positive current leaving a positive terminal, its power is less than 0, and negative power means that it is supplying current. So it is a supplier, just like this one was a supplier, and this is the only one that was absorbing energy. This could be a resistor that's absorbing energy and dissipating it as heat, or it could be a battery that's being charged.